Tonight, we're going to peel the sun like an onion. Not with your hands, of course, just with your imagination. You don't need to move. You don't need to remember all the names. You can let the words drift past you like clouds. And if you fall asleep halfway through the journey, that's perfectly fine. The sun will still be there, layer after layer, doing its job. Start by picturing the sun the way you usually see it. A smooth, bright circle in the sky, almost too simple. Just a flat disk of light. But in reality, it isn't flat and it isn't simple. It's a giant sphere of hot gas and plasma, with different regions inside it, each with its own role to play. From the outside, it looks like a single glowing object. On the inside, it's a layered machine. Well, travel from the center outward, like we're zooming through a cross-section of the sun. Imagine the scene as if you're floating in space, looking at a perfectly sliced sun, glowing softly, cut open so you can see everything inside. In the very center of that slice is the core. The core is where the magic happens. It's the heart of the sun. If you could somehow teleport there, which you really wouldn't want to do, you would be surrounded by temperatures around 15 million degrees Celsius. That's not just hot the way a stove is hot. It's hot in a way that's almost impossible to relate to. Hot enough that atoms themselves are stripped apart into bare nuclei and electrons. Hot enough that hydrogen atoms are squeezed so tightly they fuse together and become helium. In the core, gravity has pulled so much material inward that the pressure is beyond anything we can create on Earth. Every layer above is pushing down, compressing the material below it. That crushing weight and extreme temperature give the sun enough power to overcome the natural repulsion between protons. Under normal conditions, those tiny positive charges would push each other away. In the core, they don't have a choice. They are forced so close together that they fuse. When hydrogen nuclei fuse into helium, a tiny bit of mass disappears and turns into energy. That energy is released in the form of high-energy photons and particles. This is where the sun's light begins its journey. You can think of the core as an engine constantly running, steadily converting hydrogen into helium and mass into energy, second after second, year after year, for billions of years. Now imagine a single photon being born in that core, a little packet of light. You might expect it to shoot straight out of the sun, like a bullet leaving a barrel. But inside the sun, nothing is that simple. The core is so dense, so crowded, that the photon doesn't go very far before it bumps into something. It gets absorbed, then re-emitted, scattered in a random direction. Then it travels a short distance again and hits something else. Over and over and over. Surrounding the core is the next layer, the radiative zone. The name gives you a clue. This is where energy is transported outward, mainly by radiation, by those photons bouncing and zigzagging through the dense plasma. You can picture the radiative zone as a long, slow, crowded hallway. Our little photon tries to get out, but it's like trying to push your way through a stadium packed shoulder to shoulder with people who never stop moving. Every time you think you're going straight, someone bumps you sideways. Because of this endless bumping, a photon can take tens of thousands, even hundreds of thousands of years to travel from the core to the outer edge of the radiative zone. Not because the distance is so huge on a cosmic scale, but because the path isn't straight. It's random, constantly interrupted. What began as a very high-energy photon gets absorbed and re-emitted many times, gradually shifting to lower energies along the way. By the time the energy finally escapes the radiative zone, it's not quite the same as when it started. As we move outward, the conditions slowly change. The density drops, the temperature decreases. Eventually, we reach a point where radiation is no longer the most efficient way to move energy. The sun switches to a different mode. We enter the convective zone. If the radiative zone is a crowded hallway, the convective zone is a cosmic pot of boiling soup. In this region, hot plasma from deeper inside becomes buoyant and rises toward the surface, like hot water bubbling up in a pot on the stove. As it rises, it gives off energy, cools down, and then sinks back down again. Up, then down, over and over. This circular motion is called convection. You can picture giant cells of hot gas slowly rolling over on themselves. These convective cells are huge, some the size of continents, some even larger. They move on timescales much slower than your eye would ever see. But over hours and days, they churn and stir the outer layers of the sun. This churning also helps twist and tangle magnetic fields, contributing to the sun's magnetic activity and the sunspots we see on its surface. When the rising plasma in the convective zone reaches the top, it releases energy that finally becomes the light we see. That top boundary is what we call the photosphere. The word photo means light. The photosphere is the apparent surface of the sun, the part that looks like a smooth, bright disk when you glance at it from Earth. But if you could zoom in with a very powerful telescope and see the photosphere in detail, it wouldn't look smooth at all. You'd see a grainy, mottled pattern, like a boiling pot seen from above. Those grains are called granules, and each one is a convective cell of hot plasma. The centers of the granules are slightly brighter, where hot material is rising, and the edges are slightly darker, where cooler material is sinking. Each granule can be about the size of a small country. The surface of the sun is constantly regenerating these patterns, with granules appearing and fading on the time scale of minutes. The temperature in the photosphere is still incredibly high, around 500 degrees Celsius. But compared to the core, it's much cooler. This is where most of the visible light that reaches Earth originates. When you look at sunlight shining on a wall or coming through your window, you're seeing the outer layer of that convective system, the final skin of the star. If we keep going outward, we pass through something called the chromosphere. This layer is thinner and less dense than the photosphere, and it glows with a reddish color when seen during a solar eclipse with special instruments. The chromosphere is harder to notice with the naked eye under normal conditions, but it's a real layer with its own dynamics, full of spicules and jets of material shooting upward and falling back, driven by magnetic fields and waves. And then, beyond that, we reach one of the strangest features of all, the corona. The corona is the sun's outer atmosphere. It stretches millions of miles into space, a faint, pearly halo extending well beyond the visible disk. You don't usually see it, because the bright light from the photosphere overwhelms it. But during a total solar eclipse, when the moon blocks the sun's surface, the corona suddenly appears, like ghostly rays flowing outward in all directions. Here is the really weird part. The corona is far less dense than the lower layers, but its temperature is actually hotter than the photosphere. While the surface of the sun sits around 500 degrees Celsius, the corona can reach temperatures of 1 to several million degrees. It sounds backwards. You'd expect the temperature to drop as you move away from the core. But instead, after falling from the core through the radiative and convective zones to the photosphere, it spikes again in the corona. We don't fully understand every detail of why this happens, The leading ideas involve the sun's magnetic fields and waves transferring energy upward, heating the corona in complex ways. It's like the sun is quietly hiding a super hot, ultra-thin veil of gas around itself, kept warm by magnetic vibrations and tiny, explosive events too small to see directly. From the corona, some of the sun's material flows outward continuously into space as the solar wind. That wind stretches out through the solar system, carrying bits of the sun's plasma and magnetic field far beyond the orbit of Pluto. In a way, the corona and the solar wind are the sun's breath, slowly exhaled into the darkness. Earth lives inside this invisible breath, shielded by its own magnetic field. If you pause and zoom out now, you can see the whole structure in your mind as one continuous system. At the center, the core, the nuclear engine, where hydrogen fuses into helium. Around it, the radiative zone, where energy crawls its way outward through endless scattering. Then the convective zone, where hot plasma rises and cool plasma sinks, stirring the sun like a simmering pot. Above that, the photosphere, the glowing surface of light. Then the chromosphere, a more delicate reddish shell. Then the corona, a faint, hot halo stretching into space and dissolving into the solar wind. Each layer is different, but none of them can exist without the others. If the core stopped fusing, there would be no energy to send outward. If the radiative and convective zones didn't transport that energy, the surface would grow cold and dark. If the upper layers weren't shaped by magnetic fields and heat, the corona and the solar wind would look very different, and space weather around Earth would change. The sun is not just a ball of gas. It's a structured, organized star, and every layer is part of a quiet, constant flow of energy. There's one more thing to notice in this layered picture. Even though we talk about these regions like they're cleanly separated, the reality is more blended and dynamic. The boundaries are not sharp lines. They're transitions. The sun isn't a stack of rigid shells. It's more like a set of overlapping zones in a living, breathing object. Temperatures and densities change gradually. Magnetic fields loop and twist through multiple layers. Waves ripple from the interior to the outer atmosphere. As you rest, you can imagine yourself drifting slowly from the center of the sun all the way out to its edges. In the core, it's pure energy and crushing pressure. In the radiative zone, it's an endless random walk for photons. In the convective zone, it's slow, rolling currents of plasma. In the photosphere, it's bright granules and dark sunspots. In the chromosphere, thin jets of gas rise and fall. In the corona, delicate tendrils of hot plasma reach out into space, faint but fierce. And then, far away, on a quiet planet orbiting this layered star, there's you, lying down, listening, breathing. The warmth that keeps your planet's oceans liquid and your nights not too cold began in that core, threaded its way through those layers, crossed space, slipped through your atmosphere, and eventually, somehow, became part of your life. You don't have to remember the names of the layers or the exact temperatures. All you really need to know is that the sun is not a simple, flat disk. It's a deep, complex structure, balanced and steady, with each zone passing energy outward. When you feel sunlight, you're touching the last stop in a long, layered journey. As your eyes get heavy, you can picture the sun as a glowing cross-section in the sky, a calm core, a slow radiative zone, a rolling convective zone, A bright photosphere, a thin chromosphere, a hot, ghostly corona, a star with depth, a star that keeps you warm from millions of miles away. And while you sleep, that layered star will keep running its quiet engine, sending out light, keeping the solar system together, and marking time in the simplest way possible, one steady glow, one layer at a time. We're going to talk about the sun's recipe. You can imagine the sun as a giant cosmic soup. Instead of vegetables and spices, it's filled with atoms. If you could somehow freeze a spoonful of the sun and bring it safely into a lab, not melting the spoon, not vaporizing the lab, ignoring all the practical problems, and then ask, "What's in here?" the answer would be surprisingly simple. For something so huge and powerful, the sun is made mostly of just two things. The first, and by far the most abundant, is hydrogen. Hydrogen is the simplest element in the universe. One proton, one electron. That's it. It's like the basic Lego block of matter, the smallest building brick that still counts as an atom. In the sun, hydrogen accounts for about 3/4 of the mass. If you lined up all the atoms, hydrogen would dominate the crowd. The second major ingredient is helium. Helium is the product of fusion in the core, but it was also present when the sun formed. Each helium atom has 2 protons and usually 2 neutrons in its nucleus, with 2 electrons in orbit. It's still relatively simple, but it's heavier than hydrogen and more finished. In a sense, helium makes up most of the rest of the sun's mass, around 1/4. So right away, you have this picture: about 74% hydrogen, about 24% helium. That's already 98% of the sun, nearly all of it. The remaining 2% is everything else: oxygen, carbon, nitrogen, neon, magnesium, iron, silicon, and a handful of other elements. In astronomy, there's a funny habit. Everything heavier than helium is called a metal, even if it's not a metal in everyday terms. So, in a star, carbon is a metal, oxygen is a metal, and so on. To an astronomer's eye, the sun is made of hydrogen, helium, and a tiny sprinkling of metals. It's that tiny sprinkling that helps tell the sun's story. Those heavier elements didn't come from nowhere. They were forged in earlier generations of stars, in their cores and in their explosive deaths. Long before our sun existed, other stars lived, burned their fuel, and died, throwing their enriched guts out into space. That material floated in interstellar clouds, mixed and cooled, and eventually collapsed to form new stars and planets. Our sun is a second or third generation star, born from recycled stardust. The hydrogen and helium are mostly ancient, dating back to the early universe. The heavier elements are hand-me-downs from older stars. But how do we actually know this? We can't scoop up the sun. We can't land on it. We can't bottle a sample. The answer is, we read its light. When sunlight passes through a prism or a diffraction grating, it spreads out into a rainbow: red, orange, yellow, green, blue, indigo, violet. To your naked eye, that rainbow might look smooth and continuous. But if you look at it through a more precise instrument, something called a spectroscope, you see something different. The rainbow is streaked with thin, dark lines where certain colors are missing. Those lines are the sun's fingerprints. Every element absorbs and emits light at specific wavelengths, specific colors. When atoms in the sun's outer layers absorb light, They remove those particular colors from the spectrum, leaving behind dark gaps. When they emit light, they add bright lines at the same locations. By carefully measuring where those lines appear, scientists can figure out exactly which elements are present in the sun and how abundant they are. This technique, called spectroscopy, is like reading a barcode. Instead of black bars on a product in a store, we have dark or bright lines on a spectrum. Each element writes its own pattern. Hydrogen has a very distinctive set of lines, especially a strong one in the red part of the spectrum known as the H-alpha line. Helium has its own pattern. Sodium, calcium, iron all have their unique signatures. What's beautiful is that this method doesn't just work for the sun. It works for distant stars, too. From light years away, we can look at a star's spectrum and say, this one is mostly hydrogen and helium, with a little iron and calcium. Or, this one has a higher fraction of heavier elements. We can compare different stars and learn about their ages and histories. Stars with more heavy elements likely formed later in the universe, after many generations of star formation and death. Stars with fewer heavy elements are like fossils from an earlier cosmic age. The sun's chemical makeup tells us it's not one of the very oldest stars, but it's also not especially young. It belongs to a middle generation, with enough heavier elements to form rocky planets like Earth. Those heavier elements are what make planets solid and complex. Carbon in your body, oxygen in the air, silicon in rocks, iron in your blood, all of that came from earlier stars, delivered to the cloud that spawned our sun. Now, slide back for a moment to that spoonful of solar soup. Because the sun is so hot, atoms aren't really intact the way they are in a cool gas on Earth. The sun's material is in the state we talked about before, plasma. In plasma, electrons are stripped away from nuclei. It's not a gentle, tidy gas with atoms floating quietly. It's a charged, dynamic mix of free electrons and bare nuclei. But even in that chaos, the basic identity of the ingredients doesn't change. A hydrogen nucleus is still a hydrogen nucleus, a single proton. A helium nucleus is still 2 protons and, usually, 2 neutrons. When light interacts with this plasma, it still carries the signatures of those elements. This is part of what makes astronomy so elegant. We can't touch most of the universe directly, but we can watch how it emits and absorbs light. And from that, we can tell a story about what it's made of. Let's go a little deeper into hydrogen, because in a way, it's the star of the show, literally. In the sun's core, hydrogen is the fuel for nuclear fusion. Billions of tons of hydrogen nuclei slam together every second. Because of the extreme temperature and pressure, 4 protons can, through a series of interactions and particle exchanges, ultimately combine to form a helium nucleus. Along the way, some of the mass is converted into energy. That energy is what powers the sun's light and heat. If the sun didn't have such a huge supply of hydrogen, it couldn't shine steadily for billions of years. The reason our star is so long-lived is partly because it started off with so much hydrogen and because it uses that fuel at a controlled, balanced rate. Bigger, hotter stars burn their fuel much faster and live shorter lives. Smaller, cooler stars sip their fuel slowly and can outlive the sun by trillions of years. Our sun sits in a comfortable middle ground, plenty of hydrogen, a moderate burn rate, a stable existence. As fusion continues in the core, helium gradually builds up. At this stage in the sun's life, there's still a lot more hydrogen than helium in the core, but the balance is slowly changing. Over billions of years, the sun's core will become more helium-rich. That will affect how the fusion proceeds and eventually lead to the later phases of the sun's life, when it starts swelling into a red giant. But for now, it's still in a long, steady middle age, mostly hydrogen, steadily creating helium and shining a constant light. The trace elements, the metals, play quieter roles in the sun's life, but they're still important, especially in how the sun's light interacts with its outer layers. Some of these heavier elements are very good at absorbing and re-emitting light at specific wavelengths. They help control how energy flows through the sun's atmosphere. They also give rise to some of the features we see in the spectrum. In a way, they're like spices in a dish. They're not the bulk of the meal, but they change its flavor, its texture, its complexity. If you look at the sun's spectrum closely, you can identify lines from iron, magnesium, calcium, sodium, and others. These are the same elements you find in everyday life: iron in your blood and in buildings, calcium in your bones, sodium in salt. There's something quietly satisfying about that. The same ingredients that make up skyscrapers and seashells and human bodies also float in the sun, dissolved in its plasma. The universe doesn't have one set of materials for stars and another for you. It's all one shared inventory. We can also compare the sun's composition to that of the planets. The gas giants, like Jupiter and Saturn, have a lot of hydrogen and helium, more similar to the sun's overall mix. The rocky planets, like Earth, are made mostly of heavier elements. That's part of why they're dense and solid instead of being huge, puffy spheres of gas. When the solar system formed, the lighter elements tended to stay farther out in orbit, forming gas and ice giants, while heavier elements clumped together closer in, forming compact, rocky worlds. What's interesting is that without that tiny 2% of heavy elements in the sun's original cloud, none of this structure would exist in the way we know it. No Earth, no oceans, no iron cores, no silicon crusts, no carbon-based life. A small fraction of material made a huge difference in the possible outcomes. The sun's chemical recipe wasn't just about making a star. It was about creating the right conditions to make a complex solar system around it. As you lie there, you can think of yourself as part of that recipe. The hydrogen in the water in your body, the oxygen you breathe, the carbon in every cell, the calcium in your bones, the iron that carries oxygen in your bloodstream. All of it exists because of nuclear processes in stars. Some of it was made in stars long before the sun. Some of it will eventually be recycled into stars long after the sun is gone. For now, though, your life sits in a quiet middle chapter of that story. Your star is stable. Its composition is well understood. Its recipe is simple but powerful: hydrogen, helium, and a dusting of heavier elements. Those ingredients, stirred by gravity, heated by fusion, and shaped by time, have created a warm bubble in space where life can exist. You don't need to remember the exact percentages. You don't need to list the spectral lines or name every element. All you really need to hold in your mind, lightly, is this: the sun is mostly simple, but simplicity at that scale is astonishing. A basic mixture of hydrogen and helium, with traces of other elements, has been enough to light up your sky, steer your seasons, grow your forests, feed your cities, and power your heartbeat. When a beam of sunlight touches your skin, it is carrying the story of those elements. It's a message from hydrogen fusing into helium, written in wavelengths of light. It's filtered through the sun's layers, shaped by the presence of heavier elements. and finally scattered by your atmosphere before it reaches you. You're not just warmed by the sun, you're reading it, quietly, without words. As your breathing slows, you can imagine the sun not just as layers of space, but as a list of ingredients on a cosmic label. Hydrogen, helium, a hint of oxygen and carbon, a pinch of iron, magnesium, silicon, everything it needs to be what it is, a long-lived, middle-aged star, ordinary by galactic standards, but extraordinary to you. By now, you've taken a slow journey through the sun's layers and peeked at its recipe. You've seen that it's mostly hydrogen and helium, with just a sprinkling of heavier elements, all stirred together in a hot, glowing ball of plasma. You know where the energy comes from. Deep in the core, hydrogen is being fused into helium, releasing light and heat. Tonight, we're going to look at something quieter and more invisible, the balance that keeps all of this from falling apart. You can think of the sun as living in a constant tug of war. On one side is gravity, always pulling inward, trying to crush the star into a smaller and smaller ball. On the other side is pressure, pushing outward, trying to make the sun expand. These two forces are locked together in a delicate, ongoing standoff. The fact that the sun looks the same, day after day and century after century, is a sign that for now, this standoff is perfectly balanced. Let's start with gravity, because it's the simplest to imagine. Gravity is the force that pulls you down toward the ground, that keeps the moon in orbit around Earth, and Earth in orbit around the sun. The more mass an object has, the stronger its gravity. The sun has a lot of mass, about 330,000 times the mass of Earth. It contains about 99.8% of all the mass in the entire solar system. All that mass is gathered in one place, so its gravity is intense. Now imagine what that gravity is doing inside the sun. Every bit of gas, every proton and electron feels a pull toward the center. The outer layers are being tugged inward by the combined mass beneath them. The inner layers are being squeezed by everything above them. If nothing pushed back, the sun would simply collapse, becoming smaller and smaller, its density and temperature rising as its own weight crushed it. This inward squeeze is not gentle. At the center, the pressure from all that overlying mass is enormous, far beyond anything we can achieve in a lab. If there were no counterforce, gravity would win. The sun would shrink and heat up more and more, and it wouldn't stay anything like the calm, steady star you see in your sky. The reason it doesn't collapse is that something pushes back, pressure from the hot gas and from the energy generated by fusion. Pressure, in this context, is just the collective push of countless particles bouncing into each other and into their surroundings. In a gas, atoms and nuclei and electrons are constantly moving, colliding, and changing direction. The hotter the gas, the faster the particles move. The faster they move, the harder they push outward. Inside the sun, the gas is not just hot, it's blazing. In the core, the thermal motion of particles is incredibly energetic. Protons are flying around at tremendous speeds, smashing into each other. Photons, those packets of light created in fusion reactions, are also bouncing around, being absorbed and re-emitted, adding to the pressure. All of this chaos creates an outward push. So at any given point inside the sun, you can imagine two arrows pointing in opposite directions. One arrow points inward, representing gravity. The other arrow points outward, representing pressure, In a stable star like the Sun, these arrows are equal in length. The inward pull is exactly matched by the outward push. This state is called hydrostatic equilibrium, hydro for fluid, static for balance. It simply means that the star isn't collapsing or exploding, it's holding steady. If you could somehow travel through the Sun and pause at different depths, you would find this balance everywhere. In the core, gravity is strong, but pressure is also incredibly strong, thanks to high temperatures and ongoing fusion. In the outer layers, gravity is weaker because there's less mass above you, and pressure is also lower because the gas is cooler and thinner. But at every layer, the two forces match each other. That's why the Sun keeps its shape. This balance is not something the Sun chose once and then locked in forever. It's dynamic. It's constantly being maintained by the way the Sun responds to slight imbalances. If something changes inside the Sun, the tug of war shifts. And when it does, the Sun adjusts. Imagine, for a moment, that the core of the Sun suddenly starts producing a little less energy. Maybe the fusion reactions slow down. With less energy being generated, the core cools slightly. That means the particles move a bit more slowly, and the pressure they exert drops. The outward arrow shrinks. Now gravity has the upper hand slightly. The core begins to contract under its own weight. As it contracts, the gas in the core is compressed even more tightly. When you squeeze a gas, you heat it up. That extra compression raises the temperature again, which speeds up the fusion reactions. The core starts to produce more energy. The particles move faster. The pressure climbs back up. Soon, the outward push strengthens enough to match gravity once more, and the core settles into a new steady state. Now, imagine the opposite. Suppose the core temporarily produces a bit more energy. The temperature rises, particles move faster, pressure increases. The outward arrow becomes slightly longer than the inward arrow. Now the core starts to expand, pushing outward against the tug of gravity. As it expands, it cools, and the fusion rate slows down, causing the pressure to drop. Eventually, gravity reasserts itself, and the expansion stops. Again, the Sun stabilizes. In this way, the Sun behaves like a self-correcting system. If fusion slows down, the star contracts a little and heats up, speeding fusion back up. If fusion speeds up too much, the star expands a little and cools, slowing fusion down. Gravity and pressure keep each other in check. You can think of it like a star-sized thermostat on Earth. A thermostat measures temperature and tells your heater or air conditioner when to turn on or off, keeping your room within a certain range. In the Sun, gravity and pressure don't measure anything. But the physics works out so that any small imbalance leads to changes that push the star back toward equilibrium. It's not conscious, but it is remarkably stable. This stability is part of the reason life can exist here. If the Sun's output fluctuated wildly bright one day, dim, the next Earth's climate would be much more chaotic. Instead, the Sun's brightness is remarkably steady on human timescales. There are cycles and variations, but the overall energy output doesn't jump around dramatically. The deep balance between gravity and pressure keeps the Sun's core burning at a nearly constant rate. On shorter timescales, the Sun does have activity sunspots, flares, coronal mass ejections, but these are surface and atmospheric phenomena, not signs that the entire star is about to collapse or explode. Deep inside, the engine runs smoothly. To feel this, you can picture a rubber ball being squeezed. If you push it inward, it pushes back. The more you squeeze, the more the ball resists. Gravity is like the hand squeezing. Pressure inside the sun is like the rubber pushing outward. The difference is that the sun's rubber isn't solid. It's an ultra-hot fluid of nuclei and electrons and photons. But the principle is similar. Compression leads to resistance. There's another kind of pressure inside the sun, too, radiation pressure. The core is so bright, so full of energetic photons, that the light itself exerts an outward push. Photons carry momentum, and when they scatter off particles in the sun, they transfer some of that momentum. It's like a constant hail of tiny, invisible ping-pong balls bouncing off everything, nudging the gas outward. In the sun, both gas pressure particles bouncing around and radiation pressure light itself pushing contribute to supporting the star against gravity. In more massive stars, radiation pressure becomes even more important, sometimes dominating the balance. In those stars, the tug-of-war is more intense and more unstable. They live fast and die young, burning bright and ending their lives in spectacular explosions. Our sun, with its moderate mass, is more sedate. Gas pressure is the main player, with radiation pressure helping out. The result is a long, steady middle age. If you zoom out even farther, you can see that gravity and pressure aren't just balancing act inside the sun, they're also responsible for its very existence. The sun was born when a cloud of gas and dust in space started to collapse under its own gravity. As it fell inward, the material heated up and the density increased. Eventually, the core got hot and dense enough for hydrogen fusion to begin. When that happened, the newly forming sun lit up from the inside. At first, gravity was winning. The cloud was shrinking. But once fusion started, pressure increased, and at some point the inward collapse was halted. The star reached hydrostatic equilibrium for the first time. From then on, it became a main sequence star, what we see today, a stable star spending most of its life in balance. You can think of the sun's life as a long conversation between gravity and pressure. In its youth, gravity spoke first, pulling material together. Then fusion and pressure responded, pushing back. Now, in the sun's middle age, the conversation is calm. Gravity says, "Come closer," and pressure says, "Not too close," and the two find a compromise. For billions of years, they've been holding that line. Eventually, though, this balance will change. As fusion gradually converts hydrogen to helium in the core, the composition of the core shifts. Helium is heavier and doesn't fuse as easily at the same temperature. Over very long time scales, this causes the core to contract and heat up further. The outer layers respond by expanding, and the sun will begin to swell into a red giant. Even in that dramatic phase, the same basic principle is at work: gravity pulling in, pressure pushing out. The difference is that the internal conditions and the type of fusion happening will have changed. But that is a story for much later. On the timescale of your life, the sun's balance is not slipping. The tiny adjustments that happen inside it are smooth, gradual, and self-correcting. Every sunrise you've seen and every sunset you'll see is powered by that hidden equilibrium, quietly maintained in a star's deep interior. As you lie still, you can imagine the sun as a breathing thing, not because it actually inhales or exhales, but because it responds to pressure changes almost like a chest rising and falling. A slight contraction here, a slight expansion there, each motion returning it to balance. On human timescales, we don't notice these shifts. We just see a constant glow. But underneath that apparent constancy is a continuous, gentle negotiation between two fundamental forces. There's something calming about that. In a universe full of chaos and violent supernovas, black holes, colliding galaxies, your local star is in a long, quiet compromise. Gravity holds everything together. Pressure keeps everything from collapsing. The result is a stable, shining sphere of plasma that heats your planet just enough, for just long enough, to let oceans stay liquid, atmospheres stay thick, and life evolve. You can even bring this image closer to home. Right now, you're lying in a gravity field, too. Earth's gravity is pulling you down, and the surface of your bed is pushing back up, supporting you. Your body doesn't collapse into the floor because forces are balanced. The air in your lungs, the blood in your veins, the tissues in your body, all of them are held in shapes defined by balances of forces. Pressure from fluids and tissues pushing outward, gravity and external pressure pushing inward. The universe seems to like balance, not perfect stillness, but dynamic equilibrium systems that can respond to changes and settle into new, stable states. The sun is one of the clearest examples of this, a star that is neither exploding nor collapsing, but quietly shining, decade after decade, because two forces keep each other in check. As your eyelids grow heavier, you can picture those two arrows in your mind, one pointing toward the sun's center, labeled gravity, and one pointing outward, labeled pressure. Equal in length, equal in strength. A simple image for a complex reality. And while you sleep, and while you dream, those arrows will keep matching each other, second after second, holding your star together in the darkness of space. You've seen the sun as a layered star, with a nuclear heart, a radiative middle, and a convecting outer shell. You've learned its recipe of hydrogen and helium, and the quiet tug of war between gravity pulling inward and pressure pushing outward. Tonight, we're going to add a new layer, not a physical one, but a hidden force that shapes what we see on the surface and far out into space. The sun has a magnetic personality. You don't have to picture equations or technical diagrams. Just let the idea settle in slowly. The sun is not just a ball of hot gas. It's a giant, churning, electrically charged fluid. And whenever you have moving electric charges, you get magnetic fields. The sun is full of both. Its entire body is plasma gas so hot that electrons are stripped off from atoms. That means you have free electrons and positive nuclei drifting and swirling around. As they move, they create electric currents. Those currents weave and twist magnetic fields throughout the sun, especially in its outer layers. Imagine the sun's convective zone again, the region just beneath the visible surface, where hot plasma rises and cooler plasma sinks, like a slow-motion boiling pot. As that plasma moves, it drags magnetic field lines with it, pulling, stretching, twisting, and tangling them. The sun also rotates, but not like a solid object. It's what we call a differential rotator. The equator rotates faster than the poles. That difference stretches the magnetic field even more, like taffy being pulled between two hands, moving at different speeds. Over time, these processes take a relatively simple magnetic field and turn it into a tangled mess. You can imagine rubber bands wound around each other, looping in and out, crossing and reconnecting. The sun's surface becomes a playground of magnetic structures, loops, arcs, and knots of field lines rising up out of the interior and diving back down again. One of the most visible results of this magnetic activity is sunspots. If you've ever seen close-up images of the sun, you may have noticed dark spots on its surface. Those are sunspots, regions where the magnetic field is especially strong and concentrated. The magnetic field in these areas interferes with the normal convective flow of hot plasma. That interference reduces the heat being transported from below, making those regions cooler than their surroundings. Cooler is relative here. A typical sunspot might be around 500 to 4,000 degrees Celsius, compared to about 500 degrees on the surrounding photosphere. Because they are cooler, they emit less light and look darker by contrast. If you could somehow isolate a sunspot in space, it would still be blindingly bright. It only looks dark against the intense brilliance of the rest of the sun. Sunspots often appear in pairs or groups, marking where magnetic field lines poke out of the surface and dive back in. You can think of them as the visible footprints of invisible magnetic loops. Above these spots, plasma follows the magnetic field lines, tracing out bright arcs called coronal loops, especially visible in ultraviolet and X-ray images. These loops are filled with hot, glowing plasma, suspended by magnetic tension. The number of sunspots on the sun changes over time. The sun follows a roughly 11-year cycle, swinging from a period of fewer spots, called solar minimum, to a busier period, called solar maximum, and back again. During solar maximum, sunspots are more numerous, and the sun's magnetic field is more tangled and active. During solar minimum, things are quieter, with fewer spots and less eruptive behavior. This cycle comes from the way the sun's differential rotation and convection reshape and rearrange its magnetic field over years. Magnetic fields on the sun don't just sit still. They store energy, and when they become too twisted or stressed, they can suddenly reorganize themselves. When this happens, the sun can release enormous bursts of energy in the form of solar flares and coronal mass ejections. These are some of the most dramatic expressions of the sun's magnetic mood. A solar flare is like a sudden, intense flash of brightness on the sun's surface, usually near sunspots. It happens when magnetic field lines rapidly reconnect, breaking and rejoining in a new configuration. This reconnection releases energy explosively, heating nearby plasma and accelerating particles to high speeds. Flares can release as much energy in minutes as billions of nuclear bombs. Yet from Earth, we often don't notice them directly. We see their effects in radio signals, X-rays, and sometimes auroras, but the sun's overall brightness to our eyes hardly changes. A coronal mass ejection, or CME, is something slightly different. It's when a huge bubble of plasma and magnetic field is hurled out of the sun's corona into space. Imagine a loop of magnetic field that becomes so distorted that it bulges outward and finally snaps, flinging a cloud of charged particles away from the sun at high speed. These clouds can contain billions of tons of solar material, racing through the solar system at hundreds or even thousands of kilometers per second. Not every flare has a CME, and not every CME comes with a big flare. But together, they form the stormy side of the sun's magnetic life. Most of these events miss Earth entirely, sailing harmlessly off into the void. But when a CME is aimed roughly in our direction and reaches us a day or two later, we can feel the effects. We call this space weather. When the cloud of charged particles from a CME reaches Earth, it interacts with our planet's magnetic field. Earth has its own magnetic bubble, the magnetosphere, which deflects most of the incoming solar wind and protects us from harmful radiation. When a strong solar storm hits, it can compress and rattle this magnetic bubble, sending waves of energy and particles into our upper atmosphere. One of the most beautiful consequences of this interaction is the aurora, the northern and southern lights. Charged particles spiral along Earth's magnetic field lines toward the polar regions, where they collide with atoms and molecules in the upper atmosphere. Those collisions excite the atoms, which then release light as they return to their normal state. From the ground, this appears as shimmering curtains of green, red, and sometimes purple light, dancing across the night sky. It's like a painting made of particles and magnetic fields, powered by the sun storms. The same processes that create auroras can also cause disturbances in technology. Strong geomagnetic storms can induce electric currents in power lines, sometimes overloading transformers. They can affect satellites, disrupt radio communications, and interfere with GPS accuracy. Airlines flying polar routes occasionally adjust their paths or communication methods during major solar events. Astronauts in space need extra protection during periods of intense solar activity because they're more exposed to radiation. Even so, for most people listening to this, space weather is something that happens quietly in the background. You don't feel the solar wind on your face. You don't see the magnetosphere flexing and pulsing. You might see a headline about a solar flare or a geomagnetic storm, or an especially bright aurora if you live far north or south. But your everyday life continues almost unchanged. That's partly because Earth's magnetic field and atmosphere are excellent shields, absorbing and deflecting the worst of what the sun sends our way. It's interesting to notice the pattern again: balance and protection. Just as gravity and pressure balance each other within the sun, magnetic fields and the structure of our planet balance each other here. The sun's magnetism creates storms and sends out particles. Earth's magnetism catches and redirects them. The result is a dynamic but mostly gentle environment at the surface, where you can lie down, close your eyes, and listen to stories about the very storms playing out above you. If you could watch the sun's magnetic field in real time, it would look almost alive. Loops of energy arching up and collapsing. Regions of intense activity growing and fading. Field lines snapping and reconnecting, releasing bursts of light and particles. It would look less like a static ball of fire and more like a slowly breathing creature, pulsing and flexing in patterns that repeat but never exactly the same way twice. Over the 11-year solar cycle, the global magnetic field of the sun actually flips. The sun has a kind of magnetic north and south, like Earth does. But every cycle or so, those poles switch places. What was north becomes south, and what was south becomes north. This flip is tied to the buildup and release of magnetic complexity inside the sun. At solar maximum, the magnetic field is most tangled, with many sunspots and active regions. As the cycle moves towards solar minimum, the field becomes more orderly again, with fewer spots. Then it builds up tension once more. Even this flipping, which sounds dramatic, happens gradually, over years. Nothing about it is sudden on human timescales. The sun's magnetic personality changes like the seasons, not like a lightning strike. The details are messy and complicated, but the overall rhythm is slow and steady. As you rest, you can imagine the sun as having two overlapping identities. One is the calm, structural sun, defined by its layers, composition, and hydrostatic balance. This is the sun that sets the temperature of Earth, the sun that powers photosynthesis, the sun you count on every day. The other identity is the magnetic sun, restless and creative, painting patterns of sunspots, flares, and auroras across the solar system. Both suns are the same object, just seen through different aspects of physics. You can also bring this idea closer to your own experience. The sun's visible light warms your skin and lights your days, but its invisible magnetic influence shapes space itself, carving out a heliosphere, a bubble of solar wind and magnetic field that extends far beyond the outer planets. Our entire solar system sits inside this bubble, somewhat protected from high-energy particles coming from the galaxy at large. In a way, the sun's magnetism is also a shield, not just a source of storms. It pushes back against cosmic rays, reducing the amount that reaches the inner planets. So, you have shields within shields: the sun's magnetic bubble around the solar system, Earth's magnetic field around your planet, your atmosphere around your world, and finally, the roof over your head. All of them together make it possible for you to lie down comfortably tonight and listen to a calm voice talk about magnetic storms you'll never feel directly. Let that picture settle. Deep inside, nuclear fusion. Around that, layers of gas and plasma. On top of that, a restless network of magnetic fields, shaping spots and flares. Farther out, a solar wind blowing through space, and around all of that, bubbles and fields protecting tiny, fragile places like Earth. You don't have to memorize what a solar flare is, or recite what CME stands for, or explain differential rotation. You can simply remember this: the sun is not just bright, it's active. It has moods and cycles. It reaches out across space with magnetic hands, sometimes gently, sometimes more forcefully. And yet, from your perspective, it still rises, still sets, still looks like the same familiar disk in the sky. As your eyes grow heavier, you can imagine the sun's magnetic field as a soft web of lines flowing out and in, looping through space, unseen but always there. Somewhere in that web, Earth is moving along its orbit, wrapped in its own magnetic cocoon. You are inside that cocoon, safe and small, listening to the slow story of a star. You don't need to do anything, just breathe, and let your mind drift along with this tiny packet of energy as it takes a very, very long trip. Let's start at the beginning. Deep in the core of the sun, where the temperature is around 15 million degrees and the pressure is crushing, hydrogen nuclei are being pushed so close together that they fuse 4 protons through a series of reactions, eventually become one helium nucleus. In the process, a little bit of mass disappears and turns into energy. Part of that energy appears as a high-energy photon, a particle of light. This isn't light you could ever see. It starts its life as gamma radiation, incredibly energetic and dangerous if you were exposed to it directly. But you're not. This newborn photon is trapped deep inside the sun, in a place so dense that it can barely move. Imagine you're that photon for a moment. You're born in the core, and you start traveling outward at the speed of light. In a vacuum, you'd cross the space between the Earth and the Moon in a little over a second. But inside the sun, you don't get very far. After an incredibly short distance, you slam into a charged particle, a free electron, a nucleus. You're absorbed. For an instant, you stop existing as a photon, your energy now part of that particle. Then, almost immediately, the particle releases a new photon, sending it off in a random direction. You can picture this as a never-ending cosmic pinball game. The photon tries to leave, gets scattered, tries again, gets scattered again. The path is not straight. It's a zigzag, a drunken walk in 3 dimensions. You travel up, then sideways, then backwards, then up again. Step by tiny step, over unthinkable spans of time. The energy works its way outward. The sun is transparent enough to let energy through eventually, but it makes light take the long way. Like an airport where every person is stopped and redirected thousands of times before they reach the exit. By the time the energy that started as a gamma-ray photon reaches the radiative zone and then the convective zone, it has been absorbed and re-emitted so many times that it's no longer gamma radiation at all. The energy has been spread out into many lower energy photons. The light's character has changed, less dangerous, cooler in a sense, though still far beyond what our eyes can see. When this energy reaches the convective zone, the process changes. Instead of being carried mainly by photons jumping from particle to particle, it's carried by moving plasma itself. Hot plasma rises toward the surface, like bubbles in a pot of boiling water. As it reaches the outer layers, it gives off energy as light. Then, as it cools, it sinks back down again. Big, slow loops of material carry the sun's energy to the visible surface. Finally, that energy reaches the photosphere, the layer we think of as the sun's surface. Here, the gas becomes thin enough that photons can escape into space without being immediately reabsorbed. Our photon may not be the same original photon born in the core. In fact, it almost certainly isn't. Its energy has been divided and shared a vast number of times. But the story it carries is the same, a tiny piece of mass from the sun's core turned into light. Now, picture the photosphere as a bright, boiling surface with granules the size of countries, each a cell of rising and sinking plasma. From every point on this surface, photons are streaming outward in all directions. Some rush off into deep space and will never hit anything. Some head inward, back into the sun, to be absorbed again. But a small fraction are lucky enough to be aimed directly toward a little rocky planet about 93 million miles away. That's where you live. From the sun's surface to Earth, there's almost nothing in the way. Space is a vacuum, so once a photon leaves the sun, its journey is easy and straight. It no longer bounces around. It simply moves at the speed of light about 186,000 miles per second on a clean, simple trajectory. At that speed, it takes just about 8 minutes and 20 seconds for light to travel from the sun to Earth. That means the sunlight falling on your face at noon left the sun a little over 8 minutes earlier. If the sun were to magically switch off, you wouldn't know right away. You'd still see sunlight for those 8 minutes, until the last photons already on their way finally arrived. As our photon approaches Earth, something new happens. For millions of miles, it has traveled through emptiness. Now, it's about to meet an atmosphere. Earth's atmosphere is thin compared to the size of the planet, like a film of fog around a ball. But to a photon, it's a busy place filled with molecules of nitrogen, oxygen, water vapor, and trace gases. As light enters the atmosphere, some photons pass straight through, some are absorbed, and some are scattered. Shorter wavelength light blues and violets is more easily scattered by the molecules in the air. That scattering sends blue light bouncing around the sky in all directions. When you look up on a clear day, you're seeing blue because that scattered light is reaching your eyes. The sky is not a solid blue dome. It's sunlight being pinged between molecules. Some of it diverted toward you from all over the sky. Longer wavelength light, reds and oranges, passes through the atmosphere more directly, especially when the sun is high. When the sun is low on the horizon, at sunrise or sunset, its light has to pass through a thicker slice of the atmosphere. More of the shorter wavelengths get scattered out, leaving a higher proportion of reds and oranges to reach your eyes. That's why sunsets and sunrises look warm and golden and red. It's the same sunlight, just filtered by a thicker path of air. Some of the sun's light, especially in the ultraviolet range, is absorbed by molecules in the upper atmosphere, including ozone. This is good for you. It means you don't get hit by the most damaging ultraviolet photons. By the time sunlight reaches ground level, it's been softened, still energetic enough to warm your skin and power photosynthesis, but filtered enough that life can survive. Now follow our photon down through the atmosphere. Maybe it comes in at noon on a clear day, straight from overhead. It passes through air, perhaps gets scattered slightly, but continues downward. Eventually, it reaches the surface. What happens next depends on what it hits. If it strikes a patch of fresh snow, much of its energy is reflected back toward space. That's why snowfields look so bright they reflect a lot of sunlight. If it hits dark soil or asphalt, it's mostly absorbed. The energy is converted into heat, the surface warms up. If the photon hits the ocean, it might be absorbed in the top layer of water, heating it just slightly. Or, if conditions are right, it might penetrate deeper, fueling currents and the slow circulation of the sea. Some photons land on solar panels mounted on a rooftop. In a solar cell, special materials encourage the energy of the photon to kick electrons loose and create an electric current. That current is then converted and sent into wires, powering lights, machines, and maybe even the device you're using to listen to this right now. In that case, energy born in the sun's core ends up flowing through copper wires in your neighborhood, turning into sound in your headphones or speaker. Many photons land on leaves. Inside those leaves are tiny factories called chloroplasts. They use pigments, like chlorophyll, to capture photons and use their energy to drive chemical reactions. Water and carbon dioxide are rearranged into sugar and oxygen. This is photosynthesis, turning light into chemical energy. The sugar becomes fuel for the plant's cells, or building material for stems, roots, and fruit. The oxygen is released into the atmosphere, where you later breathe it in. When you eat a piece of fruit, or a vegetable, or bread, or anything that came from a plant or from an animal that ate plants you're eating stored sunlight. The chemical bonds in the food are like tiny batteries, charged long ago by photons that hit leaves. Your digestive system breaks those molecules apart, and your cells use the energy to power your muscles, your heartbeat, and even the electrical signals in your brain. So, one pathway for sunlight is core fusion, photon journey, sun's surface space, Earth's atmosphere, leaf sugar, your body, thoughts and movements. Another pathway might be core fusion sunlight, ancient plants buried and compressed over millions of years into coal, oil, or gas burned in a power plant, electricity your lamp, your computer, your phone. In many cases, the energy we casually call electricity or fuel is really just very old sunlight in disguise. Right now, some of the energy that started in the sun is helping to power this recording, the circuits that made it, the devices that play it. Another part of that energy may have powered the construction of the building you're in, or the food you ate today, or the car or train or bike that brought you home. Let's make it more personal. Imagine this same photon's energy eventually becoming the electricity that charges your phone. You plug your phone in, the battery fills with energy. Later, you press play. The phone converts stored electrical energy into tiny vibrations in a speaker or into signals in your headphones. Those vibrations push against the air in your room, creating sound waves, patterns of pressure in the air. Those sound waves travel to your ears and gently vibrate your eardrums. Inside your inner ear, those vibrations are turned into electrical signals that travel along nerves into your brain. Your brain interprets those signals as a calm voice talking about the sun. If you trace the chain all the way back, the energy that made your eardrums move, that created the tiny electrical patterns in your brain, started as mass in the sun's core. Hydrogen nuclei fused into helium, released energy, sent it on a long, slow journey outward. That energy crossed space, was captured on Earth, transformed, stored, and used. And tonight, that same energy is helping you relax. You can imagine lying there in the dark, breathing slowly, while a line of cause and effect stretches from the sun's center to your pillow. Nuclear fusion, photon diffusion, an 8-minute leap across space, a fall through the atmosphere, absorption by plants, transformation into food, conversion to electricity, and finally, into sound and thought. Even the soft warmth of your room is part of this story. The air around you, the walls, the furniture, all of them have been heated, directly or indirectly, by the sun. During the day, sunlight warmed surfaces, which then warmed the air. Even if you're using artificial heating, somewhere in that chain there was likely fossil fuel or electricity, and somewhere behind those, sunlight. Our planet's climate, too, is driven by solar energy. Sunlight warms the equator more than the poles, creating temperature differences that drive winds and ocean currents. Sunlight evaporates water from oceans and lakes. That vapor rises, cools, and condenses into clouds, then falls as rain or snow. The water cycle is powered by the sun. The weather reports you hear, the storms and calm days, the snowfalls and heat waves, they're all surface details of a vast engine running on sunlight. But in your room, things are quiet. The weather is outside, the storms are far away. What you have, right now, is a small, stable environment protected by walls, a roof, and layers of atmosphere and magnetic field above that. The sun's energy has been softened and diffused by the time it reaches you, turned into gentle warmth and electric whispers. If you like, you can picture the sun as a kind of cosmic heart. With every second, it pumps energy outward in all directions, not in pulses but in a steady flow. That energy spreads through the solar system, bathing planets, moons, and comets. Earth is at just the right distance to receive a comfortable share, not too much, not too little. You live inside that flow. Your life is one tiny, intricate pattern formed by that steady stream of energy. Think again about our photon's journey. Deep in the core, millions of years wandering, bouncing, scattering. A final leap from the photosphere to space. 8 minutes through the emptiness. A moment of interaction in the atmosphere. Then absorption by something on Earth, a plant, the ground, an ocean, a solar panel. Then a long chain of transformations, until tonight. A part of that energy is here as a quiet voice, and as the comfort in your pillow, and as the warmth in your body. you don't feel any of this directly. You feel only the end of the story, a comfortable temperature, a full stomach, electric devices that work when you need them, a calm sound in your ears. But underneath daily life is this invisible river of energy, flowing from the sun to earth and back out into space as heat and radiation. As your breathing slows, you can let that image settle. You, lying still, and above you, layers of protection, and far beyond that, a star silently sending out more energy than you could ever imagine. Just a tiny fraction of that energy reaches Earth. Just a tiny fraction of that fraction touches your life. And yet it's enough to light cities, grow forests, fill oceans with life, and let you fall asleep listening to a story. You don't have to hold on to the details, the gamma rays, the scattering, the 8 minutes and 20 seconds. All you really need is the feeling that you are part of a chain that begins in the heart of a star. Your heartbeat, your thoughts. Your dreams tonight are powered by the same physics that glows in the sun's core. If you drift off now, the sun will keep working. More photons will be born. More will begin that long, slow journey outward. Some of them will arrive at Earth tomorrow morning as dawn, painting the sky with color and waking up the world again. You may or may not see that sunrise, but it will happen, right on time, powered by the same processes we've been following. You followed a photon from the sun's core all the way to your pillow. You've seen how that tiny piece of energy powers plants, machines, and even the thoughts drifting through your mind as you fall asleep. Tonight, we're going to step back a little and look at something you live inside every day, but rarely feel directly, the way the sun quietly shapes your sense of time. You don't have to do anything with this information. You don't have to memorize dates or angles. You can just lie there, breathe slowly, and let the idea sink in that almost everything you call time in everyday life, days, months, years, seasons, is really just a record of how your planet moves around its star. Start with the simplest unit, the day. A day is the time it takes Earth to spin once around its axis. If you picture Earth like a slightly squashed ball, that axis is an imaginary line passing through the North Pole and the South Pole. The planet spins around that line, turning you toward the sun and then away again. When your part of Earth faces the sun, you get daylight. When your part is turned away, you get night. One full spin takes about 24 hours. That's your basic rhythm. Wake up, daytime, evening, sleep, repeat. If the sun weren't there, that spin would still exist, but it would feel meaningless. The sun gives each spin structure. Sunrise as your side of Earth rotates into the light. Midday when the sun is highest in your sky. Sunset when your world turns away again. Night when you're facing the dark. The pattern of when things are bright enough to see and when things are dark and quiet is imposed by a star 93 million miles away. Now stretch your view. As Earth spins, it's also moving along a much larger path, an orbit around the sun. One full orbit takes about 365 and a quarter days. That's your year. The word year sounds like a human invention, something set by calendars and laws and traditions. But underneath all of that, a year is just one trip around the sun. Every birthday is one more lap. Every New Year's celebration is Earth crossing an invisible finish line only to start another race. If you could zoom out far above the solar system and watch from a safe distance, you'd see the sun sitting near the center and planets tracing paths around it. Earth's path is almost a circle, just slightly stretched into an oval. You can imagine your planet as a small marble rolling along an invisible track of gravity. One loop is 1 year of your life. You've done it many times already. You'll probably do it many more times. Now here's where the sun gets even more interesting. The length of a year is set by your orbit, but the seasons, the feeling of winter, spring, summer, and fall are not caused by how far you are from the sun. They're caused by how your spinning world is tilted. Earth's axis is not straight up and down relative to the plane of its orbit. It's tilted by about 23.5 degrees. You can picture the Earth like a spinning top that isn't standing perfectly upright, but leaning a bit as it spins. That lean stays roughly pointed in the same direction in space, toward a point near the star Polaris, while Earth moves around the sun. Because of that tilt, the sun's light hits different parts of Earth at different angles throughout the year. When the northern hemisphere is tilted toward the sun, sunlight hits it more directly and for longer each day. That's summer in the north. The days are longer, the sun climbs higher in the sky, and the light is more concentrated. At the same time, the southern hemisphere is tilted away from the sun. Down there, days are shorter, the sun stays lower, and the light is spread out more thinly over the surface. That's winter in the south. Half a year later, the situation reverses. The southern hemisphere leans toward the sun, the northern hemisphere leans away. Summer for one becomes winter for the other. Somewhere in between, there are times when neither hemisphere is strongly tilted toward or away. Those are the equinoxes, the days when day and night are nearly equal. You feel the results of this tilt in very human ways. Hot, bright afternoons, crisp winter mornings, the first warm day of spring, the first chilly wind of autumn. You see it in the length of shadows, the time of sunset, the angle of sunlight through your window. You might schedule vacations, holidays, and even life events around these patterns, all without consciously thinking. This is because of a 23.5 degree tilt relative to the ecliptic plane. But that's what it is. If Earth weren't tilted, there would still be day and night, and there would still be years. But there would be no seasons in the way you know them. Every day at a given latitude would have roughly the same length of daylight. The sun would rise and set at nearly the same angles all year. Life would adjust to a more uniform pattern. The rhythm of planting and harvesting, of bundling up in winter and shedding layers in summer, would be very different. The sun also marks out the shape of your day in other ways. When it's low on the horizon, its light travels through more atmosphere and looks softer, warmer, more golden. Around noon, when it's higher, the light is more intense, the shadows shorter, the colors harsh and bright. You might not think about the geometry of sunlight, but you feel it. Morning feels different from afternoon because, physically, it is different. The sunlight has a different path through your air, a different angle on your skin, a different effect on the world around you. Human beings have noticed these patterns for as long as there have been humans. Before clocks and calendars, people watched the sun and the stars to keep track of time. They noticed when the sun rose and set, where it rose and set along the horizon, how high it climbed at noon, how long shadows grew or shrank. They built stones and monuments that line up with the sun on special days, solstices, and equinoxes. They made stories and myths explaining why the sun's path changes during the year, why some days are longer, why some nights feel endless. Today, you probably rely more on your phone than on the sky. Your alarm goes off at a certain hour. Your calendar app tells you the date. Your work or school schedule chops the day into blocks. But underneath the buzz of notifications is a very old structure, the cycle of light and dark, the swing of seasons, the path of a tilted, spinning planet around a star. Even if you ignore the sky completely, your body and mind still respond to those rhythms. Inside you, there's something called a circadian rhythm, a roughly 24-hour cycle of biological processes. Your brain uses cues from light and darkness to keep that rhythm in sync. Special cells in your eyes detect light levels and send signals to a tiny region in your brain, which then helps regulate hormones like melatonin, telling your body when it's time to be alert and when it's time to rest. When you see bright light in the morning, especially natural sunlight, it helps set your internal clock for the day. When the sun goes down and it gets dark, your body slowly ramps up melatonin production, nudging you towards sleep. Even artificial light lamps, phone screens, computer displays can trick that system, keeping you awake a little longer or shifting your rhythm. But the original signal, the one our bodies evolved with, is sunlight changing over the course of a day. So, when you feel sleepy at night, it's not just because you've been awake for many hours. It's also because your internal clock, synchronized to the pattern of light and dark created by Earth's rotation under the sun, is gently pushing you toward rest. The sun, without ever speaking a word, is telling your body what time it is. On longer timescales, humans built calendars to track the years and seasons. The length of a year is not exactly 365 days. It's about 2,422 days. That extra quarter of a day adds up. If we ignored it, the calendar would slowly drift away from the actual seasons. After a few hundred years, June might correspond to winter in the northern hemisphere instead of summer. To fix this, we add an extra day every 4 years, February 29th, a leap day most of the time. There are some extra rules too, to keep the calendar even more precise. All of it is an attempt to make our human counting line up with your planet's orbit around the sun. When you say it's the year 2025, that's actually a statement about how many times Earth has gone around the sun since a particular historical reference point. When you celebrate a birthday, you're marking another orbit finished. You might decorate a cake, blow out candles, think about your memories. But at a basic level, you're celebrating the fact that you have completed another full circuit around your star. There are even smaller patterns tied to the sun that you might not notice consciously. For example, the length of the day isn't exactly the same everywhere. Near the equator, day length doesn't change very much with the seasons. You get close to 12 hours of daylight and 12 hours of night throughout the year. Closer to the poles, the changes are dramatic. In summer, the sun barely sets, or doesn't set at all for weeks, the midnight sun. In winter, it barely rises, or doesn't rise at all the long polar night. Imagine living above the Arctic Circle. In summer, you could walk outside at midnight and see the sun low on the horizon, casting long shadows but never fully disappearing. Your sense of day and night would stretch. In winter, you might see only a dim twilight around noon, with the sun never clearing the horizon. Yet even there, the sun is in control, shaping cycles of light and darkness that your body and mind have to adapt to over even longer periods. Earth's tilt itself wobbles slightly in a slow dance called axial precession. The orientation of the axis traces a circle in space over about 26,000 years. That means that the star our axis points to as north changes over millennia. Polaris hasn't always been the North Star, and it won't always be. This wobble, combined with small changes in Earth's orbit, contributes to long-term climate patterns called Milankovitch cycles, which are linked to ice ages and warm periods. Once again, a star and a planet's motion around it are quietly writing the story of climate and habitability on timescales far beyond any single lifetime. But for you, tonight, the relevant timescale is much gentler, the few hours until you drift off and wake up again. Between now and then, Earth will rotate a little under the sun. Somewhere else on the planet, someone will see sunrise. Somewhere, someone will watch the sun set. Somewhere, someone is standing in a field, looking up at the sky and feeling the warmth on their face. You're connected to all of those people by the same star. You share the same source of light and the same basic cycles, even if you live in very different places with different lengths of day and different weather. Whether your room is dark and quiet, or you can see a bit of city glow through the window, or you're listening with sunlight still streaming in, you're participating in the same cosmic schedule. There's something calming in realizing that time, which can feel chaotic and stressful deadlines, appointments, clocks ticking, is anchored in something so simple and regular. One spin of Earth is a day. One orbit is a year. The tilt of the axis turns those motions into seasons. The sun is not just a ball of plasma in the sky. It's the central reference point of your entire experience of time. Think about a typical year in your life. There might be holidays clustered in winter, trips or vacations in summer, maybe a birthday somewhere in between. There might be a certain month that always feels a little hard, or a season you look forward to. Underneath those personal experiences are real, physical changes in sunlight, how high the sun rises, how long it stays up, how warm it feels, how direct its rays are. Your memories are tagged not just with dates, but with light. You might say, that happened one cold January morning, or that was on a hot August afternoon, because the sun's position shaped the world on those days. As your breathing becomes slower and more regular, you can imagine your entire life laid out as a spiral path around the sun. Each loop is 1 year. Each loop is made of days, little segments of rotation. On each loop, the tilt of your world brings seasons, times of long light, times of short light, times of balance in between. Somewhere on that spiral is tonight, a quiet point where you're lying still, listening to a story about the star at the center of it all. You don't need to hold on to details like 23, 5 degrees, or 365. 2,422 days. All you really need to carry with you is the feeling that the sun is more than just a source of light. It's the metronome of your existence. It sets the pace of your days and the chapters of your years. You wake up with it, move under it, and rest when it leaves your sky. If you drift off now, the sun will keep moving through your sky, or just below your horizon. Earth will keep spinning, and your planet will keep gliding along its path, day by day, hour by hour, second by second. You'll wake up tomorrow to another segment of that orbit, another rotation, another chance to feel sunlight on your skin. For now, you can let your mind soften around a simple image, a small, tilted world turning slowly around a glowing star, and you, a tiny part of that world, breathing in rhythm with the rise and fall of light that has been repeating steadily for billions of years. You've traveled through the sun's layers, met its ingredients, felt the balance between gravity and pressure, watched its magnetic storms, and followed a photon from the core all the way to your pillow. Tonight, we're going to meet something even more elusive than light. Something that passes right through you, right now, without you feeling a thing. Ghost particles from the sun. They're called neutrinos. You don't need to imagine equations or detectors or complicated physics. Just let this idea float gently in your mind as you lie there, completely still. Trillions of tiny particles are flying through your body every second. They don't stop. They don't bounce. They barely notice you're there at all. Let's go back, once more, to the sun's core. In that blinding, crushing environment, hydrogen nuclei are fusing into helium. You already know that process releases energy that will eventually become sunlight. But the fusion reactions also produce other particles among them, neutrinos. A neutrino is incredibly light. For a long time, physicists thought it might have no mass at all. Now we know it has a tiny mass, so small that for most purposes it might as well be zero. It has no electric charge. It doesn't interact with light. It only feels two forces, gravity, very weakly, and the weak nuclear force, which lives up to its name. The result is that neutrinos hardly ever bump into anything. When a neutrino is born in the sun's core, it's like a ghost stepping through a crowd without touching anyone. Unlike a photon, which gets trapped, scattered, and delayed for thousands or millions of years inside the sun, a neutrino escapes almost immediately. It doesn't care that the core is dense. It doesn't care that there are countless particles in its way. It just passes straight through. So, while a bit of energy destined to become sunlight spends a long, difficult life inside the sun, a neutrino takes almost no time at all to get out. Within a couple of seconds of being created, it's already flying through space at close to the speed of light, heading outward in whatever direction chance gave it at birth. Some neutrinos fly off into deep space and will never come close to any planet. Others happen to be aimed at our tiny blue world. Now imagine a continuous stream of these ghostly particles racing away from the sun in all directions. This stream is constant, steady, unbroken. It's called the solar neutrino flux, and Earth is in its path. By the time these neutrinos reach us, they're spread out over a vast area. But there are still a lot of them. Every second, something like tens of billions of solar neutrinos pass through every square centimeter of your body. A square centimeter is about the size of your smallest fingertip. Just that tiny patch of your skin is being crossed by more particles per second than the number of people who have ever lived on Earth. Expand that to your whole body, and the number becomes almost impossible to truly picture. And yet, you feel nothing. Neutrinos almost never interact with the atoms in your body. They pass through your skin, your bones, your organs, your blood, as if you weren't there. They pass through the walls, the floor, the entire Earth. Most of them could travel through a thickness of lead, many light years thick, without hitting anything. If they do interact, it's by the rarest chance, like randomly throwing a grain of sand through a galaxy of empty space and happening to hit a single tiny target. So, why do we care about them? Because they're direct messengers from the sun's core. Photons that reach us as sunlight have been slowed, scattered, and changed by their long journey through the sun's interior. By the time they escape, they no longer carry a straightforward record of what's happening in the core right now. Neutrinos are different. They escape almost instantly. When a solar neutrino arrives at Earth, it's telling us about fusion reactions that happened in the sun's core just a little over 8 minutes ago. In a way, Neutrinos let us see the inside of the sun in real time. They are a live signal from the nuclear engine at the center of our star. But there's a problem. They're so ghost-like that detecting them is incredibly hard. If you want to catch a neutrino, you have to wait for one of those rare moments when it actually interacts with matter. That means building huge detectors filled with enormous amounts of material water, or special liquids, or heavy substances, and watching them very carefully for tiny flashes of light or small changes that mean a neutrino has finally hit something. Because sunlight and cosmic rays can overwhelm these faint signals, neutrino detectors are often buried deep underground, in mines or under mountains. The rock overhead blocks most of the other particles, while neutrinos sail straight through as if the rock weren't there. In the quiet dark of these underground chambers, detectors patiently wait for a neutrino to tap them on the shoulder. For decades, when scientists first built these detectors, they expected to see a certain number of neutrinos based on our theories of how the sun works. But when they counted, they found only about 1/3 to 1/2 of the expected number. It was as if 2 out of every 3 solar neutrinos had vanished on the way to Earth. This was called the solar neutrino problem, and it was a big deal. There were only a few possibilities. Either our understanding of the sun's fusion reactions was wrong, and it wasn't producing as many neutrinos as we thought. Or our detectors were missing something. Or neutrinos were behaving in some unexpected way during their journey from the sun to us. The solution turned out to be the third option, and it revealed something subtle about neutrinos themselves. Scientists eventually discovered that there are 3 flavors of neutrinos: electron neutrinos, muon neutrinos, and tau neutrinos. The sun mainly produces electron neutrinos, but as they travel through space, neutrinos can change flavor, oscillating from one type to another. Early detectors were only sensitive to electron neutrinos, so they were missing the ones that had changed. Later, more advanced detectors, especially ones that could detect all 3 flavors, solved the mystery. When scientists counted all types of neutrinos, the numbers matched the predictions. The sun was doing exactly what we thought. Fusion in its core was producing the right number of neutrinos. Along the way, those neutrinos were simply changing identity. This discovery did 2 things. It confirmed that our basic picture of the sun's interior was correct, and it showed that neutrinos have a tiny but non-zero mass, because the ability to change flavor requires that. Just by listening to these ghost particles from the sun, we learned something new about both our star and the fundamental nature of matter. Now bring this back to your everyday experience. As you lie there, you're not only bathed in a soft flood of light and warmth from the sun, you're also being passed through by a constant rain of neutrinos. They come from fusion reactions happening right now, in this exact moment, in the core. When you listen to these words, there's a small but real sense in which you are in contact with the sun's interior, not through heat, but through ghostly messengers that make almost no sound and leave almost no trace. You can imagine neutrinos as invisible threads connecting you directly to the nuclear furnace at the center of the sun. Not in a mystical way, but in a very literal physical sense. The core emits them, they pass through space, they pass through you. Most of them continue on into the cosmos, traveling for billions of years, crossing galaxies, maybe never interacting with anything again. But for a brief fraction of a second, each one shares the same space as your body. There's a quiet comfort in that. You're not just orbiting the sun at a distance. Parts of the sun's story are flowing through you all the time. You are filled with starlight that has been slowed and scattered and turned into warmth and electricity. And At the same time, you're crossed by neutrinos that slip straight out of the core, untouched. One brings you heat and light, the other brings you information. Both are consequences of the same fusion reactions. If you could see neutrinos, your world would look very different. The night sky wouldn't be dark. It would be filled with streams and currents of ghostly particles from stars and distant galaxies, from ancient explosions and cosmic events. The sun would not just be a bright disk, it would be a furious fountain of invisible rain. The Earth itself would glow faintly with neutrinos from radioactive processes inside its interior. But your eyes can't see them, and your skin can't feel them, so they pass unnoticed. And that's okay. You don't need to sense them to be part of their story. As you breathe in and out, neutrinos cross the space between your ribs, your lungs, your heart. They pass straight through the mattress and the floor and the layers of rock and metal beneath you, exiting on the other side of the planet almost as easily as they entered. The Earth is nearly transparent to them. If you could follow one neutrino on its path, it would be a smooth, straight line, barely aware that it skimmed through a star's orbiting rock. The next time you stand in sunlight, you might feel the warmth on your skin and think of photons, the particles of light that took thousands of years to escape the sun. But you could also remember the neutrinos, which escaped in an instant and reached you in just over 8 minutes, letting you know that somewhere, in a place you'll never visit, hydrogen is still fusing into helium. The sun's heart is still beating. For now, in this quiet moment, you don't have to hold on to any numbers. You don't need to remember how many neutrinos pass through a square centimeter every second or how deep the detectors are buried. All you really need is the image of ghost particles streaming through you, harmless and silent, connecting you to the sun's core in a way light alone never could. As your eyes grow heavier, you can picture yourself floating in space, the sun in the distance, Earth below you. From the sun's core, streams of neutrinos are pouring outward in all directions. They pass through your body like wind through a net. They pass through Earth, through the oceans, through mountains, through the deepest mines where detectors wait patiently in the dark. Some of them eventually leave the solar system entirely, heading out into interstellar space, carrying with them a tiny piece of the sun's story. You are small compared to the sun. You are tiny compared to the solar system, and almost unimaginably small compared to the galaxy. But the same physical laws that govern the sun's core also shape the particles passing through your body. The same reactions that power daylight also create the ghostly messengers that ignore your presence as they go their way. If you fall asleep now, neutrinos will keep streaming. The sun will keep fusing. The detectors deep underground will keep waiting for the faintest flashes of light that mean a neutrino has finally, after traveling unhindered across space and stone, touched something. You don't have to catch them. You can simply rest, knowing that in a universe full of blazing light and violent explosions, there are also quiet, nearly invisible currents, ghost particles flowing gently through you. Every second of your life, sent from the calm, steady heart of your local star. Thank you for spending this time among the stars, and for letting this story keep you company as you drift off. From here on, there's nothing you need to think about, nothing you need to solve, nowhere you need to go. The sun will keep burning, the earth will keep turning, and you can simply rest. This has been jaw-dropping space facts to fall asleep to the sun. Let the night be dark, let your mind be light, and let your local star keep watch until morning. Good night.